Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencaster. Zencaster is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencaster has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word, Breaking Math. Go to zencaster.com/pricing and use my code Breaking Math, and you'll get 30% off of your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your. People very often ask me both how and why I started my podcasting journey. Well, as an engineer, I'm frankly very passionate about math. I wanted to find somewhere to share stories of great mathematicians from Archimedes to Alan Turing and everyone in between. And for that reason, I want to tell you a little bit about my preferred hosting platform, which is Zencaster. Now, before I continue, this is usually the conversation I have with anybody who is wanting to start their own podcast. I know there are so many people out there with passions that they want to share with the world or unique knowledge that they're just looking for a platform to start with. And Zencaster is a wonderful all-in-one platform. What I mean by that is you can do your recording and your editing and use AI to create a transcript and distribute to all platforms, including Apple Podcasts or Spotify or anywhere else where podcasts are played. For anybody like me who might worry at first about what you might sound like on an audio recording, Zencaster's post-production process makes you sound really, really smooth. It automatically removes any of the ums or ahs in your recording. It removes any of the awkward pauses in conversations, and it also helps you to set the right podcast loudness and levels while reducing any background noise, all with the click of a button. It couldn't be easier. Go to zencaster.com/pricing and use my code BREAKINGMATH, and you'll get 30% off your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting and content needs. It's time to share your story.
The history of mathematics, in many ways, begins with counting. Things that needed initially to be counted were, and often still are, just that, things. We can say that we have 12 tomatoes, or 5 friends, or that 11 days have passed. As society got more complex, tools that have been used since time immemorial, such as string and scales, became essential tools for counting not only concrete things like sheep and bison, but more abstract things such as distance and weight based on agreed-upon multiples of physical artifacts that were copied. This development could not have taken place without the idea of a unit, a standard of measuring something that defines what it means to have one of something. These units can be treated not only as counting numbers, but can be manipulated using fractions and divided into arbitrarily small pieces. They can even be multiplied and divided together to form new units. So where does the idea of a unit come from? What's the difference between a unit, a dimension, and a variable? And how does the idea of physical dimension allow us to simplify complex problems? All this and more on this episode of Breaking Math. Episode 80, Physical Dimension. I'm Sophia, and you're listening to Breaking Math. With me, I have on the host and co-host of Nerd Forensics. I have Millicent Oriana.
Hey, how you doing?
And sorry.
Hey, how's everybody doing?
Yeah, I bumped Millie's microphone. And how are you doing, Jacob Urban?
I'm good. Yeah, I'm here. Let's get to the math.
So let me ask both of you, name a unit or a dimension, a physical dimension.
Hogshead.
A hogshead, yeah, which is, I believe, 31 gallons or 62.
Something like that. Like, it's a lot. I know that.
63 gallons.
That's why it's really funny. The Simpsons when Grandpa says, "I get 3 rods to the hog's head."
Yeah.
Because it's like that car burns like 60 gallons to move like 10 feet.
And actually, let's convert that. So here's the thing, and that's the thing that's cool. You know, rods to the hogshead, it's in units of what? A rod is distance, right?
Yes.
Or length, whatever you want to call that. Often in the literature, that's referred to as length, not distance. And hogshead is a measure of what?
Liquid.
Well, specifically a measure of volume.
Yeah, volume.
Because you can have a hogshead of air or a hogshead of...
Hogsheads.
Yeah, yes, you could. A hogshead of hogsheads. It would...
Yeah.
Let's never speak of the hogshead of hogshead. But you can convert this into miles per gallon because a mile is also a length. I mean, a gallon is a volume measurement. So 40 rods to the hogshead.
40 rods to the hogshead.
Which is, let's see.
He said 63 gallons.
Yeah, so
Okay.
if we know that it's 40 rods to the hogshead, it's going to be less miles per hogshead, right?
Yeah. Well, it depends actually, because it says here a hogshead of wine is 63 gallons, while a hogshead of beer is 54.
Oh yeah, but I'm just saying. Let's assume for the problem
63.
that it's 63. Yeah. What's your intuition? Is if 40 rods to the hogshead, would that be fewer miles to the hogshead or more miles to the hogshead?
Fewer.
Yeah, it's
Yeah, much
far
fewer,
fewer.
right? Oh yeah. So then what we're going to do is we're going to divide by 320. So now we're left with hogsheads and gallons. So if I have a certain number of distance per gallon per hogshead, am I going to be able to go a further distance or less distance with a gallon?
Less.
Yeah, right. So
Way
if we
less.
Yeah, exactly. So we take that and we divide that further by the number of gallons in a hogshead. So it's 40 divided by 320 divided by 63, which gets us 0.00198 miles per gallon. Which is equal to about 504 gallons per mile. Now, let's say you wanted to convert this into feet per gallon. How would you do that? Remember, this is miles per gallon. So how do we do feet per gallon?
You divide it again.
Well, would it be fewer feet per gallon or more feet per
Fewer.
gallon?
Oh, sorry, more.
Yeah,
More.
we got
more,
to be
sorry.
careful with these.
Yeah.
So we multiply that by 5,280, which means it's 10 feet per gallon.
God.
So yeah, that gives us an idea of how we manipulate these numbers. You know, as we're using multiplication division, we're kind of seeing, like, when we went from a large unit, the hogshead, to a smaller unit, the gallon, it decreased the thing that we were dealing with, right?
Yeah.
But only because it was the reciprocal. We were dividing by gallons, right?
Yes.
So we're gonna talk about why this is on this episode, basically. Jacob, you were on the episode about counting. So what can you tell us just briefly about counting?
It's basically a way to organize like a system of units.
Yeah, knowing if you have more one thing than another.
Yeah.
And what's interesting is that the history of measurement in early times, length, you have to measure length for certain things, right? If you're making a drill, for example, you're going to want the shell to have kind of the same curvature as the end of the piece of wood that you have, right?
Yeah.
Yeah.
In one of those kind of bow drills. You're going to need to measure things all the time. You're going to need to, do weight intuitively. Like if somebody, like this fish is bigger than that fish. So we use our bodies that was our first way of measuring length. Just our bodies, our eyes, things like that. Time actually was the last thing to be measured accurately because it requires a clock to be measured accurately. It wasn't really measured accurately until Greek times, where water clocks were used for court cases, which was standardized in Roman times. Have either of you heard of this?
No, that's interesting.
It was a conical vessel so that the pressure would be equal the whole time. And a court had, certain parts of the court had to last certain amounts of time on this water clock. But yeah, so the way that mass started being measured is a balance scale is one of the simplest devices you can do. You just need something rigid and two things that you can hang from it that are the same.
Like a teeter-totter.
Yeah, exactly. It's like a teeter-totter with two things hanging from it. So the Egyptians, they used what was called a devin as a standard weight in Egypt, and it was first used to kind of measure gold. One early mention of the devin talks about it's on the juridical stela from the reign of Nebuchadnezzar He had a debt of 60 gold deben, and so he gave up his governorship of El Kab, early example of buying a government office. And then in 19th dynasty, a slave girl priced 4 deben and 1 kite of silver was paid for with 6 bronze vessels, 10 deben of copper, 15 linen garments, a shroud, a blanket, and a pot of honey. So it's interesting, basically, to get all this, weight was necessary at first to measure things having to do with money.
Yeah.
Then you have the idea of a stone, which was used to measure like weights, and it was originally a 14-pound stone, which was standardized. So that is to say that all these different ways of measuring things became more and more standardized. You had the cubit, which was the length between an elbow and the tip of the middle finger.
Yeah.
But the king's cubit was interesting is that they added another hand to it, another 4 inches, because the king has to have big arms.
Yes. Yeah, because he's important. Look at how long my arms are.
Yes, we were talking about you, Noxie. That's why.
Yeah, Noxie has a king's cubit.
Yeah, the cat is meowing.
Yeah.
And the Chinese actually used a type of clock called an incense clock as well, where powdered incense was put on kind of a spiral thing around.
Interesting.
Yeah, and what was cool about it too is that if it had different periods of stuff, they could use different types of incense for different periods of time, which I think is pretty cool. Actually, I kind of wish I had that.
Yeah, they would like burn at different
So like different types of like resins.
Yeah,
and stuff.
depending
Well,
on.
not even.
Yeah.
Let me clarify actually what I mean. And what I mean is like, let's say you had, 1 cent for the first 2 hours, and then another cent for the last 3 hours. So then when you smell the set
so you
changing,
made
you
yeah.
know that the time has reached that.
That's pretty cool.
Yeah.
That's a cool little thing.
Yeah, and this kind of this continued for a while. Essentially, you have all these units being standardized over time. Eventually, getting to the point where you're standardizing other things. So not just immediate things that you can measure, such as with your eyes, such as volume, which is a cube of length. You have length times length times length is volume, or which is a derived unit, obviously from length. Or weight, but now you're measuring things such as temperature. Temperature was originally thought in like the 1500s to be something that you couldn't really measure because it was so subjective. People pointed to the idea of dry colds versus like wet colds and stuff like that. But it turns out that Newton and Romer figured that out in the early 1700s.
Oh.
The way that you measure temperature is by seeing how much your thermometric material like changes volume.
Some sort of thermometer.
Some kind of thermometer for measuring thermos. Thermo being Greek for heat. But yeah, so this is a Newton scale, 0 being the heat of air in winter at which water begins to freeze. And then and he called these degrees of heat. So then 40 degrees, you have melting point of an alloy of 1 part lead, 4 parts tin, and 5 parts bismuth, and so on. And then Romer's system was a little bit was a little bit refined based past that, because it was based on the freezing point of water being 7.5 degrees and the boiling point being 60 degrees.
Interesting.
Which it might seem a little bit weird, but 7.5 is 60 divided by 8.
Yeah.
So it does make some kind of sense, especially because this was before decimals were used all the time in science.
Okay.
And then you have metrification in the 1600s through the 1800s. And we've gotten to the point now where none of the... originally, a kilogram was this platinum weight called the kilogram. And the meter was 2 scratches on I think it was like a gold pole. Yeah, and it sounds funny, but you have to start somewhere, right?
Yeah, it's just really funny that it's just like, let's put some scratches on a pole, and that'll be the length we need. Yeah,
This is it.
And it was originally defined as 1/10,000th thousand of the equator.
Interesting.
But now it is defined exactly as the how quickly light travels in 1,299,792,458th of a second. And a second is defined as taking the fixed numerical value of the cesium frequency, the unperturbed ground state hyperfine transitions frequency of the cesium 133 atom, to be exactly 7,192,631,770 hertz. That is to say that now all of our metric units are based on things you can find anywhere in the universe, which I think is pretty cool.
I think we should just go back to using like a king It's like the determination. Like,
Yeah.
this is the size of Philip's nose.
No, we should just use King Philip as all lengths of measurement.
Let's dig up King Philip. All right, so now we got derived units. So let me just kind of go through a few of these right here with you. Do you know the difference between a dimension and a unit is?
Dimension is going to be like the it's going to be like the size of something.
You'd think so, but turns out that dimensions actually just talks about what unit is being measured, what unit you need. But the unit talks about the specific unit. So, for example, a foot and a meter are both used to measure length, and length is given the symbol L for dimensions. So they would still use the same dimension. I mean, you can even use rods, you can use miles, you can use
Meters.
you can use smoots.
Smoot? Really? That's an actual word?
Yeah, smoot was it was measured by there's this guy, what is his name? Oliver R. Smoot, who laid down repeatedly on the Harvard Bridge between Boston and Cambridge so his fraternity brothers could use his height to measure the length of the bridge. And they defined one smoot, the bridge length to be measured to be exactly 364.4 smoots.
See, that's the type of measurement systems we need.
I agree.
Yeah, so like you said, length can be foot, smoots. Let's see. We also have, so here we have velocity. But here, you see right here, LT to the -1. What that means is L divided by T. Is that clear?
Yes.
And what that means is length over time.
Yeah.
It makes sense, right? Miles per hour, meters per second, feet per second.
Yeah.
Yeah.
And then you have acceleration, feet per second, or miles per hour per second, meters per second, whatever, and so on. But the idea is that you have these certain base dimensions that you can divide all these other dimensions into, right?
Yeah.
So yeah, exactly. So I mean, even temperature, which is a base dimension, that's actually an interesting thing to bring up. Temperature itself describes the average energy of something, which you'd think would be mass times length squared over time squared, right? You'd think that since temperature can be reduced to that, you'd be able to change the units, right, and get that even to a more base unit.
Yeah.
But it turns out that it's about the macroscopic view of the system. So if temperature is not, if we're not dealing with the actual energy of the particles, we can treat temperature as an abstract quantity. And the same thing goes for example, mass and energy. There's a mass energy equivalence, but we're not going to use it in every problem. There's also an equivalence between time and space. You know, in most problems, we don't use that equivalence, right?
No, not at all.
Yeah, because I mean, we don't talk about like, you know, I'm gonna, for example, Jacob, you're about 6 feet away from me, right?
Yeah.
Which means that you're about 6 nanoseconds away from me in light terms.
Yeah.
So I was, and I'll list the sources at the end of this episode, but one of the sources I was reading talks about how in fluid mechanics, the primary or fundamental dimensions are mass, length, time, and temperature, which means that everything can be broken into these 4 things. In other areas of physics, you might even have luminous intensity, amount of substance, or electric current be base units.
Okay.
But the important thing is that you can't add a foot to a pound, right?
No.
You can multiply them. You can have a foot-pound, but you can't add them. And that's the first thing that we're going to talk about is the idea of commeasurability. When we're talking about physical quantities, we have to be able to compare them in some way, right? Physically.
Yeah.
And so, you know, it's easy to say we could add things together, but adding lengths together is different than adding weights together, right?
Yeah.
Like just physically, like, so
They're different things, yeah.
Exactly, yeah. So I'm going to do this. I'm going to give you, Millie, these 2 pencils, and I want you to express the sum of their lengths by just moving around in space. How would you add their lengths together?
I just stack them one on the other.
Yeah, right? How would you weigh the pencils against each other?
I'd hold in my hands like this, and I just pretty much use the weight against them.
Yeah, and if you wanted to add them together, you could put them both in one spot, right?
Yeah, I'd put them both in one hand.
Oh, yeah, so if we did a balance scale, we could weigh, like, you know, 2 pencils against a third that weighed as much as both of them combined, right?
Yeah.
Yeah.
If there's like a heavier pencil, yeah, I could, 2 of these and 1 of those.
Yeah, so that's how you'd show equality is by using a scale, right? If 2 weights are equal, then they will be level on the scale.
Yeah.
But if 2 lengths are equal, then they will match up geometrically, right?
Yes. Yeah, they'll both compare to one another.
Yeah, and so that means that we have a few rules. So the comparison operation, equality, must obey the identity law. So if 2 lengths are equal, to each other, and the second one is equal to a third one, then the first and the third are the same length, right?
Yeah.
Or mass or whatever unit, right?
Yeah,
Yeah.
whatever we're adding.
Whatever you're measuring, yeah.
Yeah, and also it has to not matter what order we add things in. So A plus B plus C has to be the same as B plus A plus C. These seem like, self-explanatory things, but there are certain things that don't act this way. For example, matrices, when you multiply them together, there's certain operations that just don't work that way. And then finally, if you add things together a certain number of times, so if you add it together 3 times, you have to be able to divide that back out. So those are the rules for a physical dimension. So now we have E equals mc squared is a famous equation, right?
Yes.
F equals ma. What's interesting about any physical formula, no matter what, the units have to be the same on both sides, no matter what. It sounds like something that you could take for granted, but if you actually analyze this fact about physical quantities, you get some pretty deep stuff. So just for example, Joseph Fourier, he introduced the concept of physical dimension in his 1822 book, Théorie analytique de la chaleur, or the analytical theory of heat. This is the first time that physical dimension was mentioned in any text, and this is the table from his book. We have x, which is one of the variables being dimension, 1 of length, 0 of duration, and 0 of temperature. Right?
Yeah.
We have specific conductivity, surface conductibility, capacity for heat, etc. Well, so this is a way so what's interesting is that by listing all of our different factors that we have in a problem and breaking them down, there's actually a way that we could significantly simplify most problems. So that brings us to... So we're going to talk about the Buckingham pi theorem. So it says that any physically meaningful equation with n variables can be rewritten as n minus k dimensionless parameters, where k is a number of independent dimensions. So what does that mean? So what that means is that any physical thing, so like let's say we get the period of a pendulum, right? Yeah. Or the height of a splash in in liquid. Any formula that takes in a bunch of dimensions like height, heat, whatever, and spits something else out, whether it be a frequency, a weight, a force, you can always express it as in dimensionless parameters. And dimensionless parameters are the parameters combined together. So let's explore what that means. And a pendulum swinging, right?
Yeah.
Yeah.
Let's assume that there's no air, nothing like that. We don't care about the friction of the string, anything like that. We just have a pendulum swinging. Do you know anything about the period of a pendulum, either of you? What's it dependent on?
It's the gear itself. The gear has to turn it, right?
Oh, well, not a clock pendulum per se, just like a swinging ball on a...
Isn't it something about the leverage or...
Well, we'll figure it out. Let's pretend...
It will always, it will have to, eventually, the swinging will have to go down.
Yeah.
Oh, yeah, but that's only to continue on friction. We're talking about an ideal pendulum that swings forever. So what we're going to talk about is, let's say we want to know how long the pendulum takes to swing back and forth, right? The period.
Yes.
What is that measured in?
Second.
Time.
The exact, both of you are right. The unit is seconds and the dimension is time. So let's think about certain things that might be able to affect a pendulum swing. The length of the string, obviously, right?
Yeah.
So let's write these down. So the length of the string. So we're trying to get the period in seconds. We have the length of the string. What else can we? What other?
Weight.
The weight. Yeah, the weight
The
of the
mass
pendulum.
of the string.
Well, and of the
Pendulum.
pendulum itself at the end.
Oh, that's what I mean. So not the string, the pendulum. We're assuming
Yeah.
the string is massless. So the mass is going to be measured in kilograms. It's going to be mass. Length is going to be measured in meters, and it's going to be L for length. Period is measured in seconds. It's measured in time. Let's see what else. We have obviously how much gravity there is on Earth, right?
Yeah.
Yes.
So let's so we have G, which is measured in meters per second squared, which is length times time to the -2. Anything else that we could think of that might affect this problem?
I mean, since we're taking out things like air and of that nature, like we're focused on just the pendulum itself, I think that might be it.
Yeah, I think we're good.
Alrighty, so let's take a look at this. The Buckingham pi theorem. So we have how many variables here?
4.
4 variables, right? Period, length, mass, and G. Where G is pretty much the same everywhere on Earth.
Yeah.
We're assuming. That gives us 4 variables. Now, how many base dimensions do we have here?
1, 2.
We have time. We have length.
We have mass.
We have mass.
And we have
This is just a combination of length and time, right?
Yeah.
Yeah.
All right.
So I would say 3 units.
All right, yeah. So the Buckingham Pi theorem says that we could combine this into a few into only one unitless thing, right?
Yeah.
Yes.
All right. So we have a period as being a function of mass, length, and g, right? Because we're trying to figure out the formula for period, right?
Yeah.
Yes.
Do you notice that period, length, and g, none of those have a kilogram in them?
Yeah.
The weight is the only thing with a kilogram in it.
Yeah.
Time appears both in period and g. Length appears in both in g and the length of a string itself. But the mass, if we're doing any kind of unitless thing, this has to be 0, right? We can't have mass be part of the thing because we can multiply g by the period squared and get a different quantity. We could multiply divide g by the length and get something without units. But the kilogram, there's nothing else in the problem with the kilogram.
Yeah.
So what is that? What might that tell you?
We don't need it.
Exactly. Yeah. Exactly. Turns out that the mass of the thing in the pendulum does not matter. And what's fascinating is that we got to that with dimensional analysis, not by scientific measurement, right?
Yeah.
And that's the power of dimensional analysis, really, is that you can simplify these problems to much simpler problems. All right, so we're trying to get period out of length and g right now.
Yes.
So we need a second out of a length and g, which is length per second squared, right? So if we take length and divide it by g, we're left with seconds squared, right?
Yes.
And obviously we'd have to take the square root of that because we need to get back to regular seconds, right?
Yeah.
And that's actually one of the things that's interesting about dimensional analysis is you always need unless you're doing some weird fractal stuff, which I don't know how to do, but that honestly sounds like something I should look into. You're going to want a whole number or at least rational number fractions because basically you just have to always get the dimensions to match up. And as soon as you get the dimensions to match up, you know what affects what. So now we're going to do a problem together for the Buckingham Pi theorem. And how about we do the problem of, let's say you throw an object into a liquid, how high does it splash? Do you want to do that problem?
Yeah. Yeah. I can do
Absolutely. That sounds great.
All right. So let's say, let's say we have a few things that matter. Let's say the radius of the object, right? So we have the radius of the object. That must matter, right? Because if something is 10 times the radius, it can cause a different splash, right?
Yeah.
Yes.
The mass of the object, we say the velocity of the object, the density of the medium, the viscosity of the medium, and the height of the splash.
Yeah.
So it turns out that the way that you make dimensionless quantities out of that is if we take the viscosity multiplied by the radius squared, divided by the velocity, and divided by the mass of the object, you get a dimensionless quantity. If you take the density of the medium multiplied by the radius cubed and divided by the mass, you get another dimensionless quantity. And then finally, the height of the splash divided by the radius of the object is another dimensionless quantity. So we get here is this formula. H over R is some function of these two independent quantities. W R squared over VM and PR cubed over M. It might seem like we're just reordering variables around, right?
Yeah.
Yeah.
But what's interesting is that this actually tells us some fundamental truths about the problem. So, for example, since it's a function of these two variables, right? No matter what, if this stays constant, and while this stays constant, this is not going to change, right? Nothing else.
No.
Here, if we make the medium twice as viscous, we'd have to have twice the mass to have the same splash.
Yeah.
And that tracks, right?
Yes.
Yeah.
Now we could actually redo the problem with a completely different set of dimensions. Radius of the object, density of the object this time, right? So this time, because now the radius and mass we're assuming a spherical thing. So radius and mass would give us the density, right?
Yeah.
Yes.
But now we're just treating the density as a separate quantity itself, and we've got rid of mass as a quantity.
Yeah.
And it turns out that this actually simplifies our problem slightly, you see?
Yeah.
Yes.
And it turns out that it's a function of the ratio between the viscosity, between the density of the medium and the density of the object. As long as that stays constant, the problem, the splash will stay the same height.
Yeah, it should stay the same exact height.
No, that makes sense.
Oh yeah, and And notice this could be any formula with these two things. So I mean, it could be as complex as we want because, the sine of something tells you goes from an angle to basically how far something is from the center of the circle sideways, right? I mean, not the sine, the cosine.
Yeah.
Yeah.
But you can't take the cosine of a meter because the cosine formula is if you break it down. Okay, so like x plus minus x cubed divided by 3 factorial plus x to the fifth divided by 5 factorial minus. So you have all these different powers, and we can't add like a kilogram to a kilogram cubed to a kilogram to the fifth, right?
No.
And that's why when we're actually like dealing with physical quantities, we can only really add, divide, square, take square roots, do that thing with algebraic things. And what's interesting here that I wanted to bring to your attention.
Oh yeah, you're revising the formula and making it more simplistic.
This is how the variables shook out with exactly with the new set of variables. That's the new it shakes out differently. But yeah, so you simplify the formula by sometimes trying different sets of variables.
Yeah.
Yeah.
And when you get something that doesn't make sense, that's actually that's usually physics' way of telling you forgot a variable.
Yeah.
You forgot something that matters. And that's another huge benefit of using dimensional analysis.
Yeah.
Yeah, because you sit there going, this doesn't make sense. That's not right.
Yeah, if it doesn't add up, then you
Yeah.
know something's wrong.
Yeah, and exactly, yeah, and the Buckingham-Pike theorem, the way that you get these new variables is it's actually the rank of the dimension matrix. So remember earlier I was showing you that list of numbers from that paper.
Yeah.
Yeah.
It turns out that if you treat this like a matrix and you see how many linearly independent factors it has, that turns out to be the number of dimensionless quantities that you can have. Oh yeah, and I was also gonna say that that the base quantities. So let's say we have a problem where we have something. One of the variables is force, which can be broken down into kilograms times meters per second squared. And the other variables of importance are, let's say one of them is mass and one of them is acceleration, right? F equals ma. Okay, let's just use that. The base units of that formula aren't, there's not 3 base units. You might think there are because of kilograms, meters, and seconds, right?
Yeah.
Yeah.
But it turns out that because on one side you have kilogram times meters per second squared, and on the other side you have kilograms and meters per second squared. So the fact that you can't really break these down further, like I can't get a second out of this, right?
Yeah.
No.
Like I can't divide these units to get a second, and that's basically the definition of a base unit in any problem. It's not about the actual meters and seconds; those can help us find it, but it's about how many actual physically independent things there are, whether that be force or even a more derived quantity, like moment of area or something weird.
Yeah.
This is a really, really useful thing. Millie, were you on the episode about back of the envelope estimations? No, I think that wasn't you. But yeah, this can be used with back of the envelope estimations. So like if I reduce the problem into a bunch of simpler problems, I can do stuff like play with balloons in the sink and be like, oh, okay, that's how a submarine might work or something like that.
Yeah.
It allows us to really so if we have 6 different variables and we need to kind of like test the different numerical quantities that matter, we're hit with the curse of dimensionality, which means that let's say if you just wanted to have 10 samples in each direction, you get 10 times 10 times 10 to like 6 times, which is 1,000,000 different samples. But if you could reduce it to 2 dimensionless quantities, the number of samples that you need to really get a good idea of how the problem works goes down to 100.
Okay.
Oh, yeah, that makes sense.
Yeah, so ultimately it just makes things simpler
Exactly,
and easier to work. Like, it makes these big, gigantic, like, problems simpler and easier to work on.
Oh yeah, exactly. Yeah, and the problem in one of the books that I I'm referencing, I'll give the name at the end of the episode. It talks about the problem of throwing a ball against a wall, and how much, and if the ball's covered in ink, how big is the spot on the ball compared to the ball itself.
Yeah.
The spot on the wall. I mean that from the ink.
Yeah, the splash and all that.
Yeah, and as you can see here, he takes all these different variables, e, rho, whatever, and reduces it to 2 variables, and you can see how they behave in terms of one another.
It'd be great to live in like the 1700s and just dip a ball in ink and throw it at a wall and say I'm a mathematician.
No, this is more recent stuff. This is actually it's the utility.
1800s.
Okay, it goes back to the 1600s, but the utility of this stuff really got big, and people like Feynman during like the atomic bomb. They used to do this thing where you had 10 seconds to give somebody a math problem. They had 10 seconds to answer it with one digit of accuracy.
Yeah.
Which is 10, 10 different numbers. So you just little like exercises like that, and kind of just our full understanding of units, and just kind of like our fuller understanding of mathematics in the 20th century really led to this coming into this is big stuff now comparatively.
Yeah.
I mean, one interesting thing about Oppenheimer is that when the atomic bomb went off, he dropped a handful of paper. The paper shards blew away, and he was able to calculate the approximate megatonnage of the bomb within a few seconds before all the calculations were given.
Wow. Yeah, just by looking at the paper blowing.
Yeah, he saw how far the paper blew.
Yeah.
Oh, and really quick, I'm just going to talk about the steps of the Buckingham Pi theorem. So, let's say you have n relevant variables and m independent dimensions, right?
Yeah.
So you have these parameters that you want to talk about the relationships between. What you do is you choose m scaling variables. So just variables that represent just like base variables. So you choose like a few of them that are linearly independent. And there's going to be a guarantee that you're going to be able to find m because it's the amount of linearly independent rows and columns, the rank of the matrix.
Yeah.
So it's guaranteed to exist. And then for each of the n minus m remaining variables, what you do is you multiply them by each of those variables. So you go through the variables and you make them unitless. And that's the procedure. That's the entire procedure to determining the pi groups, is what they're called.
Okay.
Physical dimension allows us to talk about the world in terms of numbers. This was the basis of physics, since physics is just math about the world around us. We've explored how dimensions can be reduced to dimensionless quantities, and the power that this gives us to talk about seemingly hopelessly complex physical problems in straightforward terms. I'm Sophia, and this has been Breaking Math. The big source we used for this episode today was The Physical Basis of Dimensional Analysis by Ain A. Sonnen, and the lectures by David Apsley from the University of Manchester on his website. I would give both of those a check out if I were y'all. Millie, Jacob, what did you think?
Well, if I ever need to know, the radius of, an ink ball splashing on a wall, I think I now have the tools I need to figure it out.
Yeah, if I want to know how big the splash is going to be from that artificial lake I'm going to make filled with maple syrup, and when I chuck bowling balls in it all day, I can figure out how big the splash is going to be.
And you can call yourself a physicist.
And I can call myself a physicist for doing it.
Oh, one important thing, actually, that I forgot to bring up on the main episode, but you kind of brought up here is... this only helps us in as much as we know how to measure quantities, right?
Yeah.
So, if we don't know the units for viscosity, talking about viscosity won't help us, right?
Exactly.
Yeah. Oh, yeah. So it's just one of the... another thing we didn't quite talk about is that sometimes if you include too many variables in your analysis, you get too many dimensionless quantities, and that can make the problem complex again. So it's all about, playing around with, it's all about trial and error in math and science.
We're back to the scales of trying to find a balance.
Yeah, that is the scale-related term, isn't it?
Yeah.
Trying to find a balance. Any last thoughts? I already asked that. Good night, everyone.